As discussed in class today, this video is serving as a small extension of our lesson. There was one point that we did not get to, and that was to begin to quantify energy. And so instead of looking at energy as blocks and ignoring the amount of energy, a literal amount, we're going to start to look at that. Your first few problems on your homework continue to deal with energy as a qualitative phenomenon. So to get you warmed up, looking at our bar charts and where the energy is and how much proportionally of that energy is in those places. 4 and 5 deal with using that same idea, but now overlaying it with actual numbers to solve for unknowns. There are 3 energy equations that you need to know and you need to take note of. Ordinarily, I'd have you derive them in class, but time, unfortunately, is not on our side. The first, for elastic potential energy, we actually derived in class a while ago. We noticed that for a spring, if I look at the area under a force and displacement curve, that we find the amount of energy in that spring. And this is true for all elastic objects, that the spring constant, this ratio of force to distance, amount of stretch, multiplied by the how long or how far it's been stretched or compressed, squared, and then multiplying that by a constant half, gives the amount of elastic energy in a spring. It could also be in a stretchy band, and other elastic materials. We have an equation for kinetic energy, which looks very similar to this one. You may have noticed that up to this point, kinetic energy is, of course, based a lot on velocity, but it turns out that there is a relation with kinetic energy to how massive an object is. You may recall from the ball drop station that when I had a very small ball, so the tiny marble, that it didn't make nearly as much of a spot on the thermomat as did the very massive ball. And that is due to the fact that mass matters when it comes to the amount of kinetic energy in an object. Okay? Finally, we have one more equation, and that's the equation for gravitational potential energy. Here, it turns out that, again, mass is a factor in how much gravitational potential energy an object has. This gets multiplied by this factor that we call g, which I'll talk about in a second, and how high vertically something has been displaced. Now this factor here, g is the gravitational acceleration of our planet. All of our situations will occur on Earth, so therefore little g will always be 9.8 meters per second. If you went onto Jupiter or the Moon, this factor would change and we'd have to pay attention to that. Now with these equations in mind, I want to give an example of a problem and how we would apply these equations to it. So I'm going to use a very simple example, and actually there's a problem kind of like this on your homework. Let's suppose that I have a spring that's been tightly coiled, and there's a block, of course, that's actually touching the spring. And let's say the block has wheels. Okay? The cart has a mass of 100 kilograms, and it's initially at rest, so its velocity is 0 meters per second. Okay? this spring here, we'll say is compressed. So compression, or distance compressed, is delta x. We'll say that it's compressed, I don't know, 0.5 meters. And the K value for the spring is 1,000 newtons per meter. Okay. Now, sometime later, the spring releases, so now it's become uncoiled, so its delta x is 0, and now the cart rolls away. Still hasn't lost any mass, but it rolls away at some unknown velocity. We want to try and solve this velocity. Okay? So the first thing I want to do is I want to set up a bar chart. Okay? And I want to set it up to compare the energies here in situation A to situation B. Okay, so this will be bar chart for A, and then likewise I'll look at a bar chart for B in a moment. Okay, there's a couple things. First, this is kind of silly, but these are called LOL charts. In a moment we'll look at the energies, but I want to talk about this center circle because it's very important. Inside this circle is where we list all of the objects in the system. And what I mean by system is that it's all of the objects that will contain energy. Okay? We pick the system. So for this situation, I'm going to pick the Earth. Earth should always be in our system. I'm going to pick the cart. I'm going to pick the spring. And I'm going to pick the track too, or ground sometimes. And by the way, this is going to be frictionless, just to save ourselves some headache. Okay, so let's break this down. The cart's not moving, so therefore its kinetic energy is going to be 0. I can pick its 0 point, so I'm going to call this point on the track y equals 0, height, so its gravitational potential energy is 0. Its elastic potential energy, oh, well, there's definitely some elastic potential energy here. So, since that's the only kind of energy that I can see, I'm going to assign all of my energy 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'm going to apply 10 blocks of energy. Again, qualitative. Okay? Then the system changes. Energy is transferred from the spring to the cart. And so I get a change. Here in my B, I have 0 compression, so I can come down here. My elastic potential is now 0. The height of the cart hasn't changed from A to B, so this is still 0. And since it's frictionless, there's no dissipated energy, so all of my energy comes into kinetic. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, great. This is what you've already done. Now let's take it one step further. I can use this information to say, well, if all of the energy stored in the spring transfers to kinetic, then an equation, a qualitative energy conservation equation, would be that the elastic energy here is equal to the kinetic energy here. Well, that's pretty helpful. because now I can start to put in some numbers that I know. I'm going to remove this. Okay. So I'm moving over here. I have an equation for elastic potential energy. It's 1/2 the spring constant multiplied by the amount of stretch squared, and that's going to equal the kinetic energy equation, 1/2 mv squared. And then I can solve for unknowns. Notice that they both have a half, so those cancel algebraically. And now I start to put in some numbers. I have 1,000 Newton per meter multiplied by delta x squared, so 0.5 squared will be 0.25 meters squared, and that equals the mass of the cart, which is 100 kilograms, times velocity squared. I want velocity. Okay, 1,000 times 0.25, let's see, that'd be 1, 2, 3, so that's going to be 250 Newton meters, which is equal to 100 kilograms times velocity squared. I divide 100 over, that makes this 2.5. And the math gets a little murky here. A Newton is a kilogram meter per second squared. So when I divide by kilograms, I'm actually left with a meter squared per second squared, which equals v squared. So I take the square root of both sides, and v equals, quick review. I start by defining my system. I point out as few objects as I can to establish where all the energy is in my system. Spring, cart, track, these are pretty typical. Earth is always part of it. I put that in the middle. Then I go and I look at situation A, and I look for all the energies that these objects might possess and what type they would fall under, and I map it out. If there had been more than one type of energy, then I distribute my blocks appropriately. Then I come over here, I do the same thing for situation B, and then I set these things equal to each other. Notice, suppose that I had had some kinetic energy in part A. The problem changes, and I have a couple of blocks here and a few less blocks there. Okay? This equation then would then change to include a second term on this side of the equation. Why? Energy must be conserved. This quantity, which I can solve for now, that I have an equation for it, plus this amount must equal the total amount on this side. That's energy conservation. And notice how that's illustrated. 10 blocks here equals 10 blocks here. The difference is that the ability to calculate the energy stored that's kinetically is different than the equation to calculate how much energy is stored elastically. Suppose that I define my system differently. Let's say that I want my system to only be the Earth and the cart, and we're still frictionless too. Okay. Notice that I'm not including the spring in my system. So when I go to do a map for A, well, the cart has no kinetic energy. The cart's at a height of 0, that's my reference, so there's no gravitational potential. And because I'm not including my spring, the cart itself has no elastic, so there's no energy in my system to start. But then, when I look at B, obviously, there's some energy. It's now moving. In fact, I could say that maybe there's 5 blocks, let's say, of energy. 5 qualitative blocks of energy. Well, that's weird. If you remember the lecture that block 2 and 3 went through, there was an example of blocks being thrown out the window. And so there were only 26 blocks in the house. Likewise, one day there was 30 blocks in the house instead of 28. This is energy entering and exiting a system. Totally valid. Here's how we make that look. In A, the cart, our system, no energy. What gives the energy to the system in part B? Clearly, it's the spring. The spring pushes on the cart, applying some energy to it. The way that I show this is by literally drawing qualitative energy blocks coming into my system. So between A and B, 5 blocks of energy enters the system. Likewise, if there had been energy in the system in A, let's suppose we look at the spring but not the cart, then energy would come out of the system. I would show blocks coming from the system out to the external world. It's a weird thought. Do your best with it. We're going to talk about quantifying this tomorrow and Thursday. But for right now, we just want to look at it qualitatively.